believe to me, yes, baby. I'm yours, and I'm gonna be yours, and here I am, baby. I'm yours, yes, you believe it, I'm yours, baby. I'm yours, the light will shine, oh, baby, I think it's all right, yeah, baby. Oh, yeah, nothing, girl, baby. Here I am, signed, sealed, delivered, baby. Here I am, signed, sealed, delivered, woo, baby. Here I am, signed, sealed, delivered, I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered, I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered, I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. Yeah. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. Yeah. I'm yours. Yes. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. The light will shine. Oh, baby, I think it's all right. Yeah, baby. Oh, yeah, nothing, girl, baby. Here I am, signed, sealed, delivered, baby. Here I am, signed, sealed, delivered, woo, baby. Here I am, signed, sealed, delivered, I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered, I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered, I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. Yeah. I'm yours. Yes. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. Yeah. I'm yours. Yes. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. The light will shine. Oh, baby, I think it's all right. Yeah, baby. Oh, yeah, nothing, girl, baby. my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours.
All right, everybody, how's it going? Welcome, welcome, welcome. Happy Wednesday. Thank you for joining us once again on one of these days here. Let me get myself set up a little bit. We got to change my window around a little so that I can still see chat. All right. So today we are streaming. We're doing our first of two streams this week, covering units 3 and 4. This is going to be conservation of energy and conservation of momentum, very familiar topics, or they have been. And so we'll be going over some AP reminders, some stuff for your note sheet, and then doing FRQs and MCQs from units 3 and 4. So let's do it. So here we are in week 8. This is our last week before the AP exam, and as for what we're doing after AP exams, we'll worry about that after AP exams. After AP exams, because this week does culminate on Monday, May 11th. Monday, May 11th is the day of the exam, so hopefully that's not news to you. So we'll stream twice, both on Wednesday and on Friday. I'm still working my way around to grading the progress checks. I got to kind of find a good workflow for that, but I will get those done as soon as possible. For this week, some things that you need to do. Hopefully you have already tested out the AP exam demo. Hopefully you've already tried out the AP exam demo. It's just a little site where you can go and just check out your setup, and they've got some kind of bogus questions and and everything like that, and you can practice uploading things. You really got to practice that workflow because you don't want to be doing that for the first time on Monday with your AP exam, yeah. So there is also a preparation checklist which you should look at, just making sure you've got all the things that you need. There's not a submission link up for it, but I'll talk about this a little bit in a second. I do want to see a picture of your notes sheet, and I will throw you a couple points for that, for having a notes sheet ready to go for the exam. This week, we're finishing up our backwards review by doing units 1 and 2, kinematics and forces, those FRQs. We'll go over those on Friday. So, keep working on those. We're going over the 3 and 4 today. If there's any MCQs you want to go over from any of those progress checks, I've reopened all of them, so go take a look at those. I'm assuming the official AP live stream is doing a lot of review, and that's going to be really, really good for you. So, and then, yeah, so on Friday we'll stream again at the same time. Here we go. So this is our last week before the AP exam, and again, as for what we're doing next week, we'll figure that out next week. So we're actually streaming twice this week. We're doing streams on both days. So double the Mr. Bates. And again, as a reminder, our exams are on Monday, May 11th. The mechanics exam at noon and the E&M exam at 2 p.m. So please make sure that you get those done. Those are Eastern Standard Times, by the way. If for whatever reason you're going to be taking the exam in a different time zone, those are Eastern times. So if you're, you've decamped to somewhere in Chicago or something, I don't know, make sure you're looking at the times for where you are. Okay. A couple things that are posted again on my CPS, and this is review, the testing guide, and the AP exam checklist, as well as that demo link. Couple key reminders. Check in 30 minutes early. So if our exam starts at noon, that means you should check in by 11:30. If our exam starts at 2, you should check in by 1:30 p.m. Be ready. Be there early. Don't be rushing to get stuff set up at the very last minute. don't oversleep. Set yourself an alarm. There have been people in the past, obviously, and you probably have heard some of these stories who, have overslept through AP exams, or there's a famous case last year of somebody who thought the AP Calc exam was an afternoon exam and it was a morning exam, and was at Chick-fil-A. So at the time of the exam. So I mean, you can't really go out to the restaurant anyway, but just set your alarms. Make sure you know what's going on. Practice with the demo link. Know your setup. Don't leave. The only questions you want to be dealing with on Monday are physics questions. Yes, people will sleep in accidentally. Don't let that happen. If it does happen, contact Ms. Salvato ASAP, as soon as possible. All right. Cool. Again, the exam is open note. I am busy putting together some crucial formulas that are not on the official AP formula sheet, because there are a bunch of them. Even though calculation is probably less important this year than it was in previous years because of the format of the exam, it's still worth going over. So yeah. So I'll provide that list of formulas, but I want you to compile whatever other notes you want into a brief sheet. Now, when I say brief, I didn't want to set an actual page limit on it, but if your note sheet is 15 pages long, you will run out of time looking through it. Condense it, condense it, condense it. What do you really, desperately, absolutely need to know? What are the things you really, 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 really need to know? MV squared over R is actually on your equation sheet, but also that's a good reminder. Print out the APC formula sheet. So the official physics formula sheet, print it out. Make sure you've got it, or use your pink copy, that I gave you. You can have your textbook out, but it's probably not that useful because it'll take more time than it's worth. Remember, you've got 25 minutes for question 1, 15 minutes for question 2. All right, so as part of making that note sheet, let's talk a little bit about some of the critical equations for momentum and energy, and some things that people sometimes miss. Important things are two integrals. They're both integrals of forces, so this is momentum and energy. They're both integrals of forces. It's important to remember that if you integrate force with respect to time, you get momentum, you get change in momentum, or what we call impulse. So forces over time produce change in momentum. Forces over distance produce work, which is change in energy. Work. So these are similar but very different. And people always forget this. Right? There's a lot of questions. Oh, there's a friction force equal to mu mg. How much work does it do? Well, mu mg times the distance that you travel. Make sure you can calculate work. If your forces are constant, or you can average them, then instead of having to do an integral, you can just multiply. And that's where we get, for impulse, our fat equals mav equation. F delta t, instead of F dt, force times time, equals change in momentum, m delta v. And work, again, instead of force integrated over distance, if it's a constant force, you can just do force times distance, recognizing that it does have to be the parallel component of force. This is technically actually a line integral, f dot dr. It's technically a line integral, and there is a dot product, which is why you get the parallel component only mattering. It is important to note that forces that are perpendicular to displacement do zero work. A classic example of this is if something is moving in a circle, right? And you've got that centripetal force, whatever it is, tension, gravity, whatever, keeping it in orbit. That centripetal force always does zero work because it is always and forever perpendicular to the path, because that's what it means to have a centripetal force. In the event that you've got graphs of forces and potential energy, the critical equation that is not on your equation sheet is your force is the negative derivative of potential energy. For you multivariable people, it's actually the case that forces are the negative gradient of potential energy, but it's okay. They always point downhill. Negative du dx, and similarly, the potential energy is the integral of negative f dx. It's kind of the opposite of the integral for work. The reason it's the opposite of the integral for work is kind of natural, right? If your kinetic energy is going up, your potential energy is going down. Work, by the way, does have a sign to it. It can be positive or negative. If it increases energy, it's positive, and if it decreases energy, it's negative, specifically kinetic energy. So when I lift a box against gravity, if I pick it up, I am doing positive work on it. I am putting energy into it. Gravity does negative work on it. It is trying to rob the box of energy. Similarly, the box does negative work on me. And notice that if I do positive work on it, it does negative work on me. If I give it energy, the energy has to come from me. All right. I didn't put on here, obviously, the critical things of like conservation of energy, right? You know, PEI plus KEI equals PE final plus KE final. You know, conservation of energy, conservation of momentum. Those are pretty elemental. All right. So let's get into this. We do have a bunch of 2 FRQs to go over plus some MCQs. So let's just launch right in. So we've got, this is progress check unit 3. This is conservation of energy to start with that we are going to get to here. Launch. Yes. Unintentional. Okay, so we got a ski jumper that slides down a hill. It's a hill of unknown height. And it comes down H1, comes back up 10 meters. And what we know is that when it launches off of C, it's going at a velocity of 42 meters per second, because 42 is always the answer. So the question is, what's the height H1? Well, this is a great conservation of energy problem. We start off with potential energy equal to, well, let's set this up carefully, right? We start off with mgh1, and we end up with mg times 10 meters plus some kinetic energy, 1/2 mvc squared. Now notice, of course, that m appears everywhere. If you want, you could, of course, pull the 10 meters over to the other side and rewrite it this way, mgh1 minus 10. Because you can also basically set, this is the equivalent of setting your 0 of potential energy here at C and saying, well, how far did we fall? We fell h1 minus 10. In any case, you'll notice m's everywhere, so we can get rid of the m's. And I can rewrite this that what's h going to be? H1 needs to be, well, I divide by g, so I get vc squared over 2g plus 10. All right, well, now I can pull out my calculator, and I can do 42 squared over, I'm just going to use 10 for gravity because I'm like that. I'm going to use 10 for gravity because I'm like that. And I get 42 squared. Let me just check my units. Over 2 times 10 plus 10. So I get 98.2 meters. If I'd use 9.8 instead, maybe I get a slightly higher number. I get, ooh, hello. Oh, wait. There we go. I got 100 meters exactly if I use, you know, if you use 9.8, you get 100 meters exactly. So. If you use 9.8, you get 100 meters exactly. All right. We also need to calculate, ooh, hello. The speed of the skier as it reaches point B. Well, that's really just going to be, we can do this the fast way. The velocity at B is just going to be root 2gh1. I'm going to stubbornly continue using 98.2 because that's what I calculated. So root 2 times 10 times 98.2. So root 2gh1, I get 44.32 meters per second, which makes sense. It's a little bit bigger than 42. Not a lot. 10 meters isn't a huge difference, but it's going a little faster at B than it is at C. Last but not least, C is the work done by the gravitational force on the skier as the skier slides from point A to point B, positive or negative. Well, if we want to know whether the gravitational force, the work done by the gravitational force is positive or negative, all we have to do is look at, well, there's a couple things we could look at. We could look at the dot product, right? The parallel component of gravity is going to be this mg sine theta, and it is in the same direction as the displacement, which tends to give you a positive dot product. You could also look at it as just it's increasing, you know, Fg is increasing kinetic energy, and, you know, the dot product is greater than 0, so it's positive. It's increasing the kinetic energy. All right, so for the first three, A, B, and C, let's take a look at the points breakdown. A is a 2-pointer, 1 point for using conservation of energy and 1 point for doing it correctly. And like I said, if you use 9.8, you get exactly 100 meters. So 2 points there. 2 points for part B. Again, another point for using conservation of energy and then substituting incorrectly. So you get that there, which looks pretty good. It's worth noting that you actually get the same answer here, whether you used 9.8 or 10, which is an interesting thing. Part C is just a single point for a correct justification. So, again, kinetic energy is increasing, or gravitational force is in the same direction as the displacement, therefore it does positive. Okay, so 5 points so far. Now things get a little bit different, and we're doing some other stuff. So finally, we launch off the ramp, 42 meters per second is VC. And we're told that it's 25 degrees above the horizontal. We want to calculate the kinetic energy of the skier at the highest point in the trajectory. So here's a little dose of kinematics for us, right? We do this whole trajectory. At the highest point, right, we always want to ask ourselves what's happening at the apex. And here we got to remind ourselves that at the apex, the y component of our velocity is 0, only the y component. So in that case, we still have some velocity left, but it's only Vx. So what we need to do is calculate that Vx. Calculate Vx, that's going to be Vc cosine 25. And here I got to make sure that my calculator is in degrees mode. So I'm going to go ahead and do 45 cosine 25 and get 38.1, which makes some sense because, yeah, it's a little less than 42. It's pretty close to 42. And then all I got to do is calculate my kinetic energy. Ke is 1/2 mv squared. Looking up, of course, what the mass of my skier is. The mass of my skier is 80 kilograms. 1/2 times 80 times Vx squared. And I get a lot. 57,000 and a bunch. 57, almost 957.5 joules. Quite a lot of kinetic energy left. A big old dose of kinetic energy left there. All right, then we get to some more projectile motion-y stuff, which asks us to calculate the horizontal distance from the point directly before, yeah, so that one, I'm not sure why you would get a different answer there. I'm not sure why you would get a different answer there. Maybe you rounded or cosines or stuff. Maybe you did sine instead of cosine. I don't know. In any case. Now we need to calculate the distance that we go. And here's where things get a little tricky because we need to calculate, in fact, exactly, it should be 42 cosine 25. So check that. we need to calculate this horizontal distance. The problem with that is we'd like to be able to do Vx times time. But finding the time can be a little challenging. We actually don't have enough information in the x direction to find time. So naturally, we go to the y direction. In this case, I'm going to use the distance formula, right? So I want to end up at a final y position of 0. I want to start at a y position of 10. I start off with a positive velocity of VC sine 25 times delta t minus 1/2 g t squared. So basically I'm doing some parabolic motion, trying to figure out when I hit the ground. In this case, you've got a calculator, you've got Desmos presumably. So I'm going to go ahead and just grab my Desmos here and figure out when it hits the ground. Because if there's one thing you know about me, it's that I love me some Desmos. So we can go y of t equals 10 plus 42 sine 25, and let's just make sure that I'm in degrees, t minus 5t squared. I'm just committing here to t being 10 for myself. And I find that it takes about 4 seconds and a bit to hit the ground. Takes about 4 seconds and a bit for it to hit the ground for me. Here it is. Yeah, 2 meters per second is not that big a deal. That's worth like a point at most, so I wouldn't stress. I wouldn't stress. So I got my total time of flight is about, for me, is about 4.044 seconds. And again, here I would just be very clear if you're using 9.8, if you're using 10, how you got that. And then I can just plug that in up here and get, you know, my Vx, my 38.1 meters per second, you know, times 4.044 seconds, and 49. And mine went about 150 through, let's round it up, about 154 meters. Something like that. Went quite a ways. Last but not least, it asks us if the angle is increased to 35 degrees, will the new horizontal distance traveled by the skier be greater than, less than, or equal to the answer from part E1? You could calculate it again. I don't, strictly speaking, recommend it. But you know, you could just go ahead and calculate it again. Okay, well, if I bump it up to 35 degrees, it takes a while longer to hit the ground. And my assumption is it's a little further. Yeah, further. So I think it's further that, although I think further makes a lot of sense. Oh, no, 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 no! Go away, sorry. Greater than. Because again, even though Vx will go down a little bit, your x velocity decreases a little bit, time of flight goes up a lot. Time of flight increases a lot. And you can calculate it out. You know, if you've done this before, it takes just a second to calculate it, but it should be greater than. D is a 2-pointer. So again, indicating speed uses the horizontal component and a point for correctly substituting in. So 2 points there for part D. part E is 3 points. The first part for calculating that distance, 158 meters, 154, right? They used 9.8. I used 10, so mine's not going to go quite as far. 3 points there. Again, for calculate, you got to calculate the time in the vertical direction, and then solve for delta t. Again, I don't know that they'll ask you to do this on the exam this year because of the format of the exam, but if they do, don't be shy about using your calculator or whatever. You can always say, hey, I used my calculator to get this answer. And then you calculate the horizontal distance, some good old projectile motion. E2, 2 points greater than with a justification. Yeah, typically the 45-degree thing, 45 degrees being the furthest, 45 degrees is the furthest if you're firing from ground level. The higher up you go, the flatter you want your trajectory to be. But 10 meters isn't that high, so getting closer to 45 is still better. All right, now we get some other stuff. After landing, the skier slides along the horizontal ground before coming to a stop. So let's draw some horizontal ground. The skier's initial speed on the ground is the horizontal component of the skier's velocity when the skier left the ramp. So it starts off with kind of a Vx0, still 80 kilograms. Starts off at x equals 0, and then it slides at some distance d before coming to a stop. And the idea is that as it slides, it's subject to a frictional force, a coefficient of friction that actually increases with distance, which is a little strange. So it kind of starts out not very rough, and then gets like rougher and rougher and rougher as you go. So the coefficient of friction increases. Well, we can work this out. The force that it will experience is going to be a kinetic friction force. So it'll be mu mg. And in this case, because mu changes, it will be 0.2 mgx. So the bigger that our x value is, the more that it'll go. In that case, and what do we know about d? At d, right, it stops. So what we need is we need this force to do a certain amount of work, and the amount of work we need it to do is equal to the initial kinetic energy of the object. So we'll get 1/2 m Vx0 squared equals, and in this case, to do that work, we need to do an integral from 0 to d of our force. We need to integrate our force because our force is always changing. X dx. All right, now in this case, you will still notice that the m's cancel out, so let me get rid of the m's. They don't matter. We'll do our integral, and we'll end up with, well, I know how to integrate x, so we'll end up with 0.2 g, and we get a 1/2 x squared from 0 to d. Quick note that the 1/2s also cancel. So what we end up with here is that our initial velocity squared equals 0.2 times g times d squared. Well, we happen to know what Vx0 is. It is that same 42 cosine 25. Go ahead and square that. Divided by 0.2 and divided by 10. So I get d squared equals like 724.5. And of course, if I square root that, I get, for me, taking g equals 10, I get that it slides around 26.92 meters. 0.92 meters. If you use 9.8, it should go a little further. The hardest part about this one is that you have to do an integral, and the clue that you have to do an integral is that your force is always changing. So work generally is force the integral of force over distance. You only get to do force times distance if f is constant. or you're averaging F, which you're pretending it's constant. So F is not constant, so you do have to do an integral here. All right, this one was worth 3 points, 1 for doing an integral. So 1 for using conservation of energy, for attempting to basically say, hey, friction has to rob it of all of its energy, so you're using work. 1 point for integral, and 1 point for kind of doing the integral right, doing it all, putting it all together. They use 9.8, so again, they get 27.2. It slides a tiny bit further. All right, and that is that. That is the whole question for energy. So pretty classic, conservation of energy, a little bit of work, some project, you know, it always transitions in. They love to transition into kinematics later, so you know the format of the exam will be weird, but I still expect that to happen for them to transition into this kind of thing later. All right, let's move on from conservation of energy onto conservation of momentum. So this is unit 4. So the first thing is the running experiment determined the mass of a block without a scale. So they set a block up on a surface of negligible friction, and they apply a force on it for a certain amount of time, moving along a straight line. And here's the force exerted as a function of time. At time t equals 12, the block is moving at 1.5 meters per second. Well, how could the students use the graph to estimate the impulse exerted on the block? Remember, if you've got a graph, there's only a certain number of things you're ever going to do with it. You might be looking for an intercept, you might be looking for a slope, you might be looking for area, something like that. Or you might be pulling a value off of it. In this case, impulse, remember, is defined as the integral of force over time. So probably the best thing to do is find the area under the curve. So let's go ahead and find the area under the curve. Now, notice that this thing is all bumpy. They probably do not expect you. Okay, if I were doing this, I might be a little neurotic and like trapezoid rule the whole darn thing, but that's also going to take 15 minutes. So I'm going to cheat a little bit here, and they're allowing us to estimate. And I'm going to sketch a little line of best fit. And then treat it as one big trapezoid. So it's got a height of 3 newtons on this side, a height of 6 newtons on this side. So yeah, basically they should give you a little bit more help here, but in this case they didn't. So I'm just gonna trapezoid it. So I'm estimating the area. I guess they tell you to estimate it, but still, that seems a little obtuse. So, you know, using the trapezoid rule, it's going to be 12 times 3 plus 6 over 2. So that's 12 times 4.5, or about 54 Newton seconds of impulse. The area under that curve is about 54. Calculating the mass of the block, right? Well, what does impulse do for us? It's change in momentum. So we can set that impulse equal to the change in momentum, m delta v, because we're told that it goes from rest to 1.5 meters per second. So we divide that by 1.5, and I'm estimating that the block weighs 36 kilograms, which I don't know where the students found this block. 36 kilograms is, you know, like 80 pounds. This is not a block. This is an 80-pound block. All right, taking a look at this, and obviously if you're watching this on YouTube, you can always pause and kind of go back. Part A has just 1 point for, you know, calculating the area under the curve. A2 is 2 points, 1 for figuring out some way to estimate the area. I wish they had told us a little bit more explicitly to estimate the area. And another point for correctly substituting. And then 2 points for part B for relating it to, you know, impulse to change in momentum. So there we go. And obviously, if you calculated something different for the area, you'll get something different for the mass. And that's okay. All right. So now we get to part C. when t equals 12 seconds, the force sensor loses contact with the block, which continues to move along the horizontal surface. When t equals 20, the block encounters a rough area and comes to rest in 25 centimeters. On the graph below, sketch a graph of the speed of the block as a function of time. Well, hopefully, the period from 12 to 20 hopefully makes sense. That until 20 seconds, there's no friction. After 12, we lose contact with the block, right? So I'm assuming in this region that our speed just is flat. Yeah, I'm assuming it's just flat. Afterwards, it encounters a rough area and comes to rest in 25 centimeters. If it's just normal friction, it should slow down at a constant rate because it should be subject to a constant force of, mu mg. So the only part that's really mysterious is what happens at first. Well, it starts at rest, right? And then the question is, how does it get up to speed? Notice that the force is constantly increasing. I mean, frankly, even if it were a constant force or a constant acceleration, if it were a constant force, our speed would be increasing linearly. Because the force is increasing, this part should be concave up. This first region should be concave up because the force is increasing. It's speeding up more and more and more over time. Should be constant and then slow down. So I should actually want to, and then okay, we'll do part D before we look at this. Part D, calculate the coefficient of friction between the block and the rough surface. I'm going to assume that it means 25 centimeters after 20 seconds, in which case what we can do is we can use our third kinematics equation, right? We can use V final squared equals V initial squared plus 2a delta x. We know that it comes to a rest. It starts at an initial velocity of 1.5 meters per second. And it takes 25 centimeters to do so. I'm just going to go ahead and put in 0.25 meters. So I can go ahead and calculate that. 1.5 squared divided by 2 divided by 0.25. So I get an acceleration of 4.5 meters per second. Meters per second squared, excuse me. Notice, of course, if it's subject to a force mu mg, kinetic friction force mu mg, the acceleration of that force doesn't depend on mass and is just equal to mu g. So here I'm going to take g equal to 10 and get a mu of 0.45. If you take g equal to 9.8, you get, a very slightly higher number. All right, so let's take a look at this. C is a 4-point question. 1 point for concave up in the first section of the graph, a point for a straight horizontal section, a point for a straight line at the third section, and then the last point is that the V initial is 0 and the V final is also 0. Because it has to start from rest and then stop. Part D is 2 points, one for, okay, I did it a kinematics way, they did it with work, that's fine, force times distance. Basically, some way of getting mu that works for you. Any way that works. They did it with kinetic energy, that's fine. Last but not least, we get to E for this. The students repeat the same experiment with the block with twice the mass of the original block. They exert the same average force on the block. The students once again get the block to move with a speed of 1.5 meters per second. So it's got twice the mass, an equal force, and they managed to get it to an equal final velocity, which is kind of interesting. Which of the following gives the best estimate for the time range when the new block reaches a speed of 1.5 meters per second? Well, hopefully it's clear that if they're, if you're kind of looking at this from the, F delta t equals m delta v, or, if you want to consider it as like an integral, hopefully it's clear that it should take more time, right? And in fact, in general, it should probably take about twice as much time. If it's the same average force, it should take about twice as much time. It took 12 seconds before. It should probably take about 24 seconds now, because we need twice as much momentum for that. So 2x the momentum. We need to get twice the momentum into the block, twice the mass, but same velocity. So that should be a 2. 2x the momentum, equal force, takes twice the time. And then, assuming the new block reaches the rough surface with a speed of 1.5 meters per second, is the distance it moves in coming to rest greater than, less than, or equal to the distance the first block moved on the rough surface? It should be equal to, because if you kind of look at the kinematics equation, kinematics I think here is the cleanest. V final squared equals V initial squared plus 2a delta x. It comes in with the same initial velocity, and still stops, same final velocity. And it turns out that the acceleration doesn't depend on mass here, because the force, right, is mu mg, it's kinetic friction force, which equals ma. So the acceleration of friction here is just mu times g. So that doesn't depend on mass either, so it should be equal to. So E here gets 3 points for selecting t greater than 20 seconds. So the required momentum doubles, doubling the impulse. So it should go from 12 to like 24. And then a point for selecting equal to that mass is not a factor in the distance traveled because of friction. So yeah. All right. And that takes us through both of our FRQs. I did, in our last 15 minutes, I did pull out a couple notable multiple choice questions, because again, I reopened these. I know we did these multiple choice things way back when in November or whatever, but I did reopen them for kicks. So I thought we would look at these real quick. These were ones that a lot of students had trouble with. So the elastic band launcher, so this is off Progress Check Unit 3. The students use an elastic band to launch carts of a known mass horizontally on a track. The elastic band is non-linear. So that means that instead of having a linear spring would be F equals kx, or negative kx, and having a spring potential energy, which is 1/2 kx squared. We are not that. So our hypothesis is that F is kx squared in this case. How can we collect enough data? One thing to note is that every single answer here uses the cart's maximum speed. So what is the cart's maximum speed going to be? Well, imagine if you stretch this band out and let it go, right? We're going to end up with some kinetic energy, right? So the question is, we'll get 1/2 mv squared. If we pull it back a distance x, how much energy is in it? Well, notice that I can calculate that, because potential energy is the negative integral of force over distance. So I can get the integral of kx squared is 1/3 kx cubed. And then some funny things happen, right? Notice it's asking me for what relationship can I graph. Notice here that if I do speed squared to get the 1/2 mv squared, right, versus distance cubed, I'll get a linear relationship. So that's where the cube comes from integrating the force. I know you probably haven't looked at these in a while. Right, I didn't like this question. And most of you got it right anyway. choose 7 different hiking paths. This was a subtle one. This was an annoying one. 2 hikers start from the top of the same hill. It could take different paths to the bottom. And it basically asks, what's the difference between their changes in potential energy? Lots of people said that it was the same because the height descended is the same. Remember, our potential energy from gravity is mgh, and it says that hiker A weighs more than hiker B. So UA has to be greater than UB. So that's a reading one. Gotcha. Graphs of potential energy. I wouldn't be surprised if they ask you to sketch one of these somewhere in mechanics. An object of mass m moves in one dimension, and we get a conservative force x and a potential energy graph related with it. Are the graphs consistent with one another? Well, remember that our force should be the negative derivative of this. So let's go ahead and look. In this first section, right, it's got a slope of, let's see, 2, 2. It's got a slope of -1, so my force should be +1. It is. In this section, it's got no slope at all, so my force should be nothing. Correct. Here it's got a slope of, let's see, 4. Oh, sorry, this is 3 meters. So it goes up 1 over 1, so this is +1, so this should be -1, and once again 0. So the two graphs are in fact consistent with each other and are perfectly fine. So fx should be the derivative, the negative derivative of u. We actually have another one of those here. Which of the following graphs best shows the force F? Again, we're trying to sketch the negative derivative of our graph. So a couple things to note, right? It starts off flat, so our initial force should be 0. So that right away cuts out most of the contenders. Really, it only leaves A and D. So the question is here, over here, right, U has a negative slope. That means that F should be positive. It should go up, not down. So got to be careful with that. Negative du dx. The force wants to push us to greater and greater x here. Okay. A couple more of these. Potential energy of a spring. Here's a nonlinear spring where they give us a force of negative ax squared minus b. Change in elastic potential energy. Now, one quick thing to note, we are integrating here from 0 to 2 of negative force. And the reason we're doing negative force is because we want u. You could just integrate the force and you get a negative answer, but the potential energy of the spring should increase as you stretch it out. So just something to be aware of. So we get 3x squared minus 4 dx, and then we can just do this integral. So x cubed minus 4x from 0 to 2. So really only 2 that matters. It's 8 minus, wait a minute, minus b, where x is the displacement, b equals 4, the change in elastic potential energy. Give me a second to look at this function. This is a fun one. Negative 3x squared minus 4. Yeah, what did I do wrong here? I just did my integral wrong somehow. That's fine. Negative. What the heck did I do with my integral? 3x squared. Oh, it's 3x squared plus 4. Good job, Bates. Womp womp. Well, 0 is not one of the choices. All right, excellent. 16 joules. It should be positive anyway. and again, you see a function like this, you should think about whether you want to integrate it or take a derivative. This one was also one that people got wrong a lot. We've got a ball of mass m. It falls a height h onto a spring of spring constant k. A lot of people got this one subtly wrong because the maximum compression of the spring, right? Let's say it compresses some distance delta x. In this case, the ball actually falls mg h plus delta x. And that all turns into spring 1/2 k delta x squared. So you actually have to solve the whole darn thing in this case. You actually have to solve, 0.2 times 0.3 plus x and 12.5 x squared, and see that figure out where the two intersect, which is, at a pretty small number. So they intersect at, they intersect at 2 values? That's not helpful. Oh, they intersect twice. That's great. So I have to get my calculator to do a better job here. First curve, second curve, and our guess. Yeah, point. That's very interesting. Why don't I get the right answer there? Let me think about this for a second, why I'm not getting the right answer. I know just what you tune in for. So 0.2 is the mass. Oh, I forgot to include gravity. That would be a big, that'd be a big no-no. Yep, 0.31. I forgot to include gravity. That's okay. Yep, 0.31. So just be careful to include that in solving with your calculator. Potential energy graphs always mess people up. This one was a 2 kilogram object moving under the along the x-axis under the influence of a single conservative force. When the object's at position 0, it has a speed of 3 meters per second. And the potential energy curve is shown, alpha x squared. Which of the following is correct about the motion of the object? Well, it's going to slow down as it goes up the potential energy curve. But notice, how much kinetic energy does it start with? How much energy does it actually have? 1/2 times 2 kilograms times 3 squared. It only has 9 joules of energy. So it's actually capped. It can't make it to x equals 4. It actually gets stuck at like x equals 1 point something and slides back down the hill. It doesn't have enough speed to make it to 4. That's the thing. You could also guess and check, right? If you plug it in here, the total conservation of energy needs to be the same. Real quick, a couple of these impulse ones. F equals at squared. What's the impulse? Well, we can do at squared dt from 0 to 2. And we get 8a over 3. And that's going to equal m delta v, because what's impulse? It's change in momentum. So delta v is 8a over 3m. That one's pretty straightforward. You've got to do the integral, though. Ball dropped on floor. A 2 kilogram ball is dropped from a height of 20 meters and rebounds to a height of 5 meters. So this one is a delta v question. right? Our impulse will be m delta v. The question is, what velocity does it hit with and what velocity does it come off with? Well, it comes in with a velocity of root 2g, h1, and leaves with a velocity of root 2 gh2. So I can kind of calculate that from 20 meters and 5 meters. Root 2, I'm going to take 10 because, force of habit, times 20 meters. So it comes in with a velocity of, hey, wouldn't you know it, 20 meters per second, and leaves with a velocity of 10 meters per second. Please be careful. What's our delta V if we come in at 20 and leave at 10? In this case, our delta V is 30 meters per second because we were going 20 this way, and now we're going 10 this way. So it had to be, I guess, minus 30 if you really want to be, 30 meters per second if you really want to be, got to put some signs on it. And it's a 2 kilogram ball, so m times delta V is 2 times 30, or 60 meters per second. Tricksy hobbitses. Again, block collision. This asks us to compare the impulses of two blocks in a collision. The answer was actually that they're exactly equal by Newton's third law, right? The two blocks collide in each other. They provide equal and opposite forces. And no matter what that force curve looks like, right? As long as the forces are the same, the two blocks are in contact for the same amount of time, they're going to have equal and opposite impulses. One of them gains J, the other loses J. So just please be cautious about that. They always exchange the same amount of impulse. So that's about it for today. Next time we meet on Friday, we'll be going over the unit 1 and 2, that's kinematics and forces, FRQs, to finish this out. We will finish our note sheet, and I'll be posting up some information about the note sheet, and I'll show you what mine looks like, and so you can have that. Talk about, on there, we'll also think about what are some notable graphs we want to watch out for if we get force versus time, force versus distance, whatever, and some other key concepts. Because our exam's coming up, so here we go. And with that, it's 2:30. I'm going to leave you to your own devices, and see you on Friday.